Hi everyone, in this video we'll study how to compute the runtime of recursive algorithms. Now if you're watching this video, I'll assume that you have an idea of recursive algorithms and how to construct them. And in this video, we will study how to compute the runtime of recursive algorithms. So recursive algorithm, I'm just going to call it rec function. So say this is your recursive algorithm, okay? It'll take as input the size n. So rec function n, because it is a recursive algorithm, it'll have a base case. And that will be the case which will determine where it stops. And then there will be a recursive case. So this is the general structure of any recursive algorithm. So there's be a base case and the recursive case. So now let's look at a concrete example to study the runtime. So the example that we're going to consider is computing 2 to the power of n recursively. So I will assume that most of you who are watching have some idea of how to do this kind of recursion. So if you're not familiar, we'll go over this algorithm here. So to compute 2 to the power of n, we'll call this algorithm power of n or power n. Now, we'll first talk about the base case. That is where the algorithm would stop. It would stop if n equal to 0. So that's the base case. If n equal to 0, we know that the algorithm should return 1, because 2 to the power of 0 is 1. Otherwise, which is the else statement here, what it would do is it would return 2 star power of n minus 1. So you will call power of n minus 1. So the basic idea of recursive algorithms is that you think that computing 2 to the power of n is difficult. So what you do is you try to solve a similar but smaller problem, which happens to be 2 to the power of n minus 1. And you know that if you get the answer to this problem, you can multiply that with 2 and get the solution to 2 to the power of n. Now, because it's a recursive algorithm, 2 to the power of n minus 1 will once again be called with, and it will call power n minus 2 and multiply that with 2. And this process will continue till you reach n equals 0, when you know that the problem is very simple and you can solve it, which is essentially will return 1. At this case, the recursive algorithm will start returning, and finally you will get your answer of 2 to the power of n. So this is the recursive way to compute 2 to the power of n. Of course, there's an iterative way as well. Now, in this video, we're going to study how to compute the runtime of such recursive algorithms. Now, first, what we have to do here is to determine the runtime. To do that, let Tn be the runtime of this recursive algorithm when the input size is n. Now, if n equals 0, it's going to take a constant amount of time because it's just going to return 1. So in that case, theta 1 will be the runtime of this algorithm. Now for n greater than 0, you're essentially going to have Tn minus 1 plus c, some constant amount of time. Okay. Now, how do we go about solving this runtime and getting an absolute value of Tn? So that's what we're going to solve here. So the first method which is applicable for this problem is substitution. So we'll try substitution. So substitution method is one way to find the solution to the runtime of a recursive algorithm. So what we're going to do is we're going to write Tn equals Tn minus 1 plus c for n greater than 0. Now what can we do with Tn minus 1? We can write Tn minus 1 as Tn minus 2 plus c plus c. Now, This is essentially t of n minus 2 plus 2c. Continuing this, we will have t of n minus 3 plus c plus 2c, which is essentially t of n minus 3 plus 3c. In this way, if you go forward, what you will have is t of n minus k plus kc. So Tn will evaluate to t of n minus k plus kc. Now if you substitute k2 with n, we will have t0 plus nc. Now we know that t0 is theta 1, which is given here. So that is nothing but theta 1, it's theta plus Cn, which is theta 1 plus theta n. So our Tn evaluates to theta of n in this case. So here we studied the substitution method where we kept substituting Tn with Tn minus 1 first, then Tn minus 2, and so on and so forth. And finally we got Tn as theta of n. So for this particular problem of finding power of n, we saw that substitution method works. Now let's look at another problem. The next problem that we will study is Fibonacci series. So many of you know Fibonacci series, and you also might have studied recursive algorithm to compute the Fibonacci series. So I'm not going to explain what a Fibonacci series is in detail here. We'll just look at the code and try to understand it. So basically fib n, which is the function for Fibonacci series, will be written like this. If n is less than 2, what we will do is we will just return n. Otherwise, what you're going to do is you're going to return fib n minus 1 plus fib n minus 2. So in Fibonacci series, fib n, nth number of the Fibonacci series, is the summation of the n minus 1th and the n minus 2th number. And for n equals 1 and n equals 0, the Fibonacci series is 0 and 1. So for when the fib 0 is 0 and fib 1 is 1. So that's the base case. So this is the base case here, and this one is the recursive case. So how do we go about finding the runtime of the Fibonacci series? Now to do that, Tn is the runtime of the algorithm for size n, or input size n. That will be equal to theta of 1, that is constant, if n is less than 2. That is for the base case, it will just be theta of 1. Now, for n greater than 2, it will be Tn minus 1 plus Tn minus 2. That will be the runtime of Tn, because we have called, here it should be fib, called fib n minus 1 and fib n minus 2. So that's why we have that, the runtime as well, if n is greater than or equal to 2. Now how do we go about solving this? So to find the runtime, if we try to solve this, what is likely to happen? So if we try to do it with the substitution method, let's see what happens. So let's try the substitution method, and we'll see that it'll quickly become intractable. So for substitution, one thing that we can realize is Tn minus 1 is definitely greater than Tn minus 2. So if we're going to write Tn, we will have something like this. Tn will be Tn minus 1 plus Tn minus 2, and there'll be some constant C as the amount of time, and you can, if you really want to make this precise, you can write plus C there as well. So that's the constant amount of time that you're going to take apart from Tn minus 1 and Tn minus 2. And what we can do is, we can first try substitution. But if we try substitution, what is likely to happen is this. What will happen is, if you try Tn minus 1, you have to write it as Tn minus 2 plus Tn minus 3, and Tn minus 2 will have to be written as Tn minus 3 plus Tn minus 4. Now, and there will be 2c here. Now for each of these, you'll again have to expand. So these two will give 2 terms, this one will give 2 terms. So the number of terms keeps increasing. So this is going to be very difficult and it's not possible to solve. So substitution method works when there is actually only a single term, which is what we saw here in this case. That is Tn equals Tn minus 1 or Tn. Or it could also be something like Tn equals Tn minus 2 or Tn minus 3, something like this. But if there are multiple t's in the other side, that is the right hand side, you won't be able to use the substitution method. That is why we are going to make use of this observation. Tn is greater than or equal to Tn minus 2. How will this help? Now, we cannot find the runtime precisely. So first what we're going to do is we're going to try to bind the runtime from the top as well as from the bottom. So we'll use this in this particular way. Now, so what we'll do is we'll write Tn as greater than twice Tn minus 2 plus C. So we just substitute Tn with Tn minus 1 with Tn minus 2 plus C. But because as Tn minus 1 is greater than Tn minus 2, we put a greater than or equal to sign. Now we'll continue this. Of course, a greater than, so we can now write Tn minus 2 as 2 times Tn minus 4 plus C plus C. Now this will become 2 square Tn minus 4 plus 3c, 2c plus c. Now carrying this forward, we'll have this as 2 cube Tn minus 6 plus 7c, and we will have 2 to the power 4 then as Tn minus 8 plus 15c. Now if we try to extract the general trend here, this is what we will get. In general, we will have, just using this approach, Tn to be greater than or equal to 2 to the power of k, see, times Tn minus 2k plus 2 to the power k minus 1c. Because you see this 15 is nothing but 2 to the 4 minus 1 here. So that's what we're exploiting to get the general trend here. Now, when will we reach T0? When k equals n by 2, we will reach T0. So, if we substitute this, we'll get Tn greater than or equal to 2 to the n by 2 T0 plus 2 to the n by 2 minus 1 C, which is greater than or equal to, now T0 is a constant, and just for the purpose of this algorithmic study, we're just going to substitute T0 with C as well. It's another constant, but it does not make too much of a difference because we are just looking at the asymptotic bounds here. So that will be 1 plus c 2 to the n by 2 minus c, and this will help us write it as omega 2 to the n by 2. Because Tn is greater than equal to 2 to the n by 2, the constant in front does not matter, we have an omega bound here. So we saw that we cannot do the substitution method for solving this problem, simply because substitution will create a large number of terms and become unmanageable, like this case here, and therefore we tried to bound Tn. So we've tried to bound Tn from one direction. Now let's try to bind Tn from the other direction. So once again, we can consider Tn to be Tn minus 1 plus Tn minus 2 plus c. Now we can consider the opposite direction, that is Tn minus 2 is always less than equal to Tn minus 1. And using that, we can write Tn less than equal to 2 Tn minus 1 plus c. Now continuing the substitution, we can say that is 4 Tn minus 2 plus 3c, or 8 Tn minus 3 plus 7c. So in general, we will get Tn less than equal to 2 to the k Tn minus k plus 2 to the k minus 1 times c. Now if you substitute k equals n, we'll get Tn less than equal to 2 to the n T0 plus 2 to the n minus 1 times c. Now once again, we are not going to bother with the constant, so I'm just going to assume that T0 is c. So this will give Tn less than equal to 1 plus c 2 to the n minus c. So as we are interested in the asymptotic runtimes here, we will not bother with the constants. So this will give us Tn as equal to O of 2 to the n. So using the two approaches here, what have we established? We have found the lower bound, which is omega 2 to the n by 2, and upper bound, which is O of 2 to the n. Now, this Fibonacci series also has a theta bound. Okay, so we're not going to prove the theta bound here, but I'm just going to give you the theta bound. So the theta bound is theta of phi of n, where phi or phi is the golden ratio, and that is equal to, so phi equal to 1 plus phi root 5 by 2. That is what phi is. So we found the upper and lower bounds by this method here. So what did we study in this video? So if we go back in the beginning of the video, we're trying to find out the runtime of recursive algorithms. So that's what we started. And then we first studied power of n. Now to study power of n, we studied the substitution method. And the substitution method works well when Tn is related to a single term on the other side, like Tn minus 1 or just Tn minus 2 or Tn minus 5, something like that. There are multiple terms, this substitution method will not work. And that is why we studied the Fibonacci series, where you have Tn equals Tn minus 1 plus Tn minus 2. And if you try the substitution method, there'll be an explosion of terms and you will not be able to handle it. So we try to bound it from the top as well as from the bottom, and then we got the omega and O bounds here. But there is also a theta bound for this problem, the Fibonacci series, and that is given in terms of the golden ratio. With this, I'll conclude this video. So we studied recursion and how to compute the runtime of recursion in this video. In the next video, we'll study how to use the master theorem to find out the runtime of recursive algorithms which have a particular form. Thank you for watching. Please like my videos and subscribe to my channel.